Hi everybody, we'll continue chapter 3 and we need to do 310 and 311 to finish this long chapter. And I kind of recorded this video and find out later on that the file is not good, crashed. Some parts didn't work well. So I'm just gonna redo it and use the same notes and hopefully explain some parts here. And you can, of course, pause the video or forward as needed. The same file will be posted in modules. So linear approximation, if you trace what we did so far from that beginning of chapter 2 of the tangent and how we evolved to derivatives and all that, we get now to some type of application in which we're going to use that to approximate functions near certain points. And differentials is another topic here. So there are two topics in this 310. And so to explain that this is not a new topic, of course, the linear approximation is new, but the method that we're going to use is not new. It's something that we've done in the past. I start with this, the point slope equation, where you set it up. Then, we used it that way from the tables and all that. Then we went into the derivative and we said the slope of the tangent line, and we defined actually the derivative. So if you take this equation and you solve it for y in this form, and you replace y with f of x, you get kind of linear approximation. So what we're trying to say that if we have that tangent line, and let's call it here L of x, and at this point A, and of course, if you want to use this point slope, you can consider x1 as A and f of A as y1. So if you take this here and you zoom in, right, what's going to happen is you're almost going to see a line on top of the other line, right? That's the goal. So they're almost same function there. And if they are almost same function, then we like linear functions because they're simple. Then we can use a linear function to approximate that function. So it happens that sometimes you don't even know the function, and use the whatever quantities you have to approximate the values. So that's one purpose. So this picture is familiar. So now the equation you've done in the past, now it's just linear approximation. And so we will find a kind of L of x, which is a linear approximation to a function near a point. And that's it. So that's part is easy. These linear, we also say linearization. So sometimes the question is, what is the difference? We say linearize a function. It's also linear approximation. It's also a tangent. We'll put another here, a tangent line approximation. That's you probably now, with the way we did the course, we're more familiar with now. That's a tangent line approximation. And in engineering, for example, in physics, we say linearize a function. So it's not bad. You'll see it's actually good to work on. There are some tricky parts later on, but they will get better as we do the concave and sketching and parts. So some other parts we'll talk about them briefly, but as we do more of the sketching, we'll understand these better. But when it comes to this process, it's easy. You need f of a. What is it? You need f prime of a, and you'll come up with L of x. All right. So let's look at first example. And this first example is similar to number 5 in the homework. So when you get to that, you can use the same pattern of this one. So find the linearization of this function, square root of x of plus 3 at a, which is a is 1. So remember now, we linearize and we find the approximation to a point, not anywhere, right? Use it to approximate the numbers. So once we find the approximation to this point, use that to find these values. And we're going to see what's going on here with this 405 and 3.98. Are these approximations overestimates or underestimates? That's what we're interested in as well. If you approximate something, how far is it off, or is it above or below, right? So the derivative, we see from the formula, we need to find the derivative. We use the power rule, and it gives us this 1 over 2 square root of x plus 3. So now, based on the formula, we need f of 1, because a is 1. F of 1 is 2, right, which is here. F prime of 1 is here, is 1/4. Once we have these two values, now we can put them in the that tangent line approximation. We can use all until we know that it's the same thing. And we substitute the 2 and 1/4, and we get this line, which is same as this one. So you do want to end up with the line, not the quadratic function or something like that. So that's where we know it's correct. So what are we saying here? We started with f of x as a square root of x plus 3. That's the function. We're saying now that what we come up with is exactly that function near 1. That's it. So that's what we did. Okay. Now, if we're asked for some other values, which means we, as long as it's near 1, we can use this thing. So now we're given this question. Find the square root of 3.98. So the tricky part here is 3.98. So if you want to use this approximation, it needs x. So here what's given is not x. So this 3.98 under the square root, remember f of x is x plus 3, which means 3.98 is same as x plus 3. So x here is 0.98, which is near 1, right? If x is 3.98, that's not near 1. You can still use it, but the error will be large, way too large. It's almost like there is no point of using this. So that's what you need to watch for. What is the value that you're going to use in the approximation? Is it the direct value or is it something else? So similarly here, 405 x is not 405. It's 1.05 when you match it with the function, and it comes up to 0.01. So I put here, we will see this example where it is, if the function is square root of x, then the value that you're given is the one you'll be using. All right, so there are a few things to understand from this problem, and now let's look into the graph or geometric interpretation of it. So that's where we're interested. and we found that L of x, and here is the curve, and as you see, they're perfectly matching there at the tangent, right, at that point. And as we see, this line is always above the graph. Since it is above the graph, we're going to say that it's over an estimate. The estimation here is larger or over. So that's how we determine that part. So we're going to compare whether it's over or below and say whether it's over estimate or underestimation. So of course you can use a calculator to figure out these parts, calculate these and compare them with the values we find. And of course the calculator computes the point itself, but linear approximation here gives an approximation over an entire interval, because you see we used the tangent and the point, so we're dealing there with some intervals. Here to give you an idea about these estimation, so x is 0.98. The linear approximation is this, the actual value is that. Similarly here, but if you pick, for example, a square root of 6, then x is 3. You know, now you can compare it with 1. Look at L of x is 2.5, and this is 2.44. So you can see the error. If you take these two, they're way too close compared to these. So this one is just the first digit is off there after the decimal. Here it's the same up to there, it's almost same, right? So you see now that what it means for this approximation to be or near a value, and how good it is near that value, but once it is far from that value, it is off. All right. So I think that summarizes that, and we do some examples from the homework. The second part is differentials. Differentials are also interesting, and up to now, we dealt with the operator or differential operator, which is differentiate a function with respect to, for example, x, or differentiate a function with respect to time. But we treated it as a single thing. We did not split it or anything like that. So we say dy dx is same as differentiate of f(x) with respect to x is same as f prime. But now we'll see that as we move with this thing, we become interested in some other parts. The one part we will be interested in, and it's going to be useful in the future, is to look actually to them separately. So if you have dy dx equal f prime, if we look at it as a fraction, kind of treat it now as a fraction. So before it was as a single, not a fraction, but now is treated as, so maybe we can say here after, is going to be treated as a fraction. So it has two parts. And if we multiply both sides by dx, we get this differential here, or differentials, because this is, we have a differential of y and differential of x, right? And so the differential of y becomes dependent on x and dx. And so this is the formula here, number 3, which is that. And I'll explain something about it to make it simple. We've done where we talked in the past how dy dx is taking that limit of that slope as x approaches 0, making x small, and we're still interested in x small, and how dy dx became the slope of a tangent line, and how the slope of tangent line became the derivative. So now, to make it simple and not to confuse, dy, keep in mind it is the rise of the tangent line. So that's kind of the geometric interpretation to it. It still has to do with how the function changes, the y changes. It's a small change, very small change, and we're interested to see how that changes compared to x and d of x, but it is still the rise of the tangent line. Whether, when we say the rise, doesn't mean up for sure, just whatever the change of y, right? So maybe I should put it there. That change, that small change of y, but I use the rise, so we still connected with the slope idea, so we know, make it simple. But the delta y is more of the rise or the change of the curve. So that's the difference between the two. The delta y is more of the change of the curve, and so now everything should connect and make sense. When we use dy dx, we took the limit because we wanted x approach 0, because we want to zoom in at that point, right? So now that we are interested in the differential y, it's still going to be the same thing. It's that part of change of tangent line, and dx is that change of x, right? But you see the change of x here is the same for the curve and the tangent. All right, so this is a nice application to talk about, and then we do some examples. We saw the sphere in related rates, but if now we'll talk about it in a different sense. If the radius of a sphere, let's say you have a sphere, and the radius is measured and found to be 21 centimeters, with the possible error that is at most, error max at most is 0.05. What does that mean? It means when you measure and you find you're not getting the same reading, but there is a kind of a difference between the two. But when you look into the readings, the highest you find, the difference means, for example, this differential of r, right? Just like we talk about differential of x. We find that it is 0.05. So what is the maximum error in using this to compute the value? So how does this error trickles down to the value? So that's the question. So if we take this differential of volume using of course, the sphere volume formula that we know, and we did, it's going to be 4 pi r squared dr, all right? And you've done it before, but now think about it in terms of kind of a differential, not related rates. And you use the given formulas or the given information, you'll find that dV is 277. That looks huge. We're saying dr is 0.05 and dV comes up to 77. So now, is this a huge problem or not? That's a question that we need to answer. So one thing that we do is, or done in engineering and other places, is to compare the error with the actual thing, which called the relative error. So in the relative error, we're going to compare that error, right, with the actual thing, with the volume, and see that kind of proportion there, or that ratio. So we should say the ratio there. So from previous formula, you get this, and divide, you get 3. So dV, the change, the error, the relative error, here for the volume is 3 times this relative error for the radius. All right, so the relative error for the volume is about 3 times the relative error in the radius. And that's more important, and that's more of information that can be used. And of course, you can calculate everything here and use percentage instead, just plain decimals for the error, because to have a better idea about the numbers, so we can do some calculations. So you see that these differentials are used here to get a better information, so we can take a better decision and whether that's gonna affect or not, or how to accommodate for it. So it looks like the relative error in radius, the relative error in the volume is 3 times the relative error in radius. And of course, it explains as well that it's not something to be ignored. If you calculate the error and it's way too small, 0.05, let's just ignore it. And we're using it to, work with some different tank or something that is a sphere. And, so that's important to know that the errors trickle down and how they trickle down. Now here you can see an interesting example. So we keep the same topic of differentials. Since I said this is something you've seen, we'll do number 6 before we go into linearize. And number 6 just says, well, if you have this function, find the differential of each function. So we'll use the formula, and since it's s instead x, we're going to just use s instead x. So no big deal. What you did in the past is what you do now. You find the derivative. Here you use the quotient rule, and at the end you move ds to the side, which means you multiply both sides by ds. So that's how this differential y is connected with s and the differential of s. And similarly, if you're given a function in which you need to use the product rule and the chain rule, and later on you move du to the side. All right. So you can pause the video, work on it, and match it with that. So now let's work on linearization or linear approximation, or tangent line approximation. So here is an example in which we just look at it in general. So we need, based on the formula, we need the derivative, power rule. We need f of 1, 5. We need f prime of 1, 12. We put them in the formula that mentioned at the beginning, and we get the line. So what does this mean? This means that L of x, let's do it this way. This means that x to the 4th plus 4x squared is just like 12x minus 7 near 1. All right, so the idea is not complicated, but it requires just a process. So let's look at this example here. What is the linear approximation to this number? Well, so we're going to say, okay, which function is this? So this e to power x, right? If it's e power x, what is the derivative? It's same. And now let's find the values. F of 0, e power 0 is 1. F prime of 0, e power 0 is 1. We do again the formula. Then we find that linear approximation is 1 plus x, which means the function f of x, which is ex, is same as the approximation near 0, because we did it at 0. And of course, the question is at 0.01, which is near 0. So now we can use the formula. Because we use 0 is much simpler to use, and it's near 0.01. So we use the formula, we substitute 0.01. Now it's easy to use, and we get 1.01. Of course, you can do on a calculator this and compare it to this and see how good it is, and also to verify your answer whether this thing is correct or not. Similarly, for a square root of 104 is near 100. We know a square root of 100 is 10, so we're going to go ahead and just use 100 instead. The f of x is equal to the square root of x, f prime power rule, we get this. So now we need the two values. F of 100 is a 10, f prime of 100 is 120, or 1 over divided by 20. So the linear approximation, right? So let's do it first here. The linear approximation is f of 100 plus f prime of 100 times x minus 100. And we substitute the values, and we get x divided by 20 plus 5. So we are saying that the square root of x is same as x divided by 20 plus 5 near 100, right? Consequently, when it is 104, you see we can use it directly. There is no change here. There is no plus 1 or something there. So it's just directly 100.4 is the x. And that gives us 10.02. All right, so once you do these examples, now we'll switch gear to a similar thing, but in examples where, for example, formula is not given and it's asking some additional questions. So suppose the only thing that we know is f of 1 is 3. And the graph of its derivative is this. Well, okay. So let's find what is f of 0, 9 and 1.1. So here, as you see, you're given the derivative graph. So f prime of 1, so this is a, so we need there, it's 2. We use f of 1 is 3. F prime of 1 is going to come from the graph, which is f prime of 1 is 2, and x minus 1. And then we simplify, we get L of x, or linear approximation, is 2x plus 1. And we can use it now to find for the two requests, 0.9, substitute 2.8, 1.1, substitute 3.2. So it's the same process, even if the formula is not given. If the graph is given or other information is given, it's the same process. No problem there. So now we need to connect few dots. This is where now we'll try to figure out with what we have, but later on when we do the sketching and second derivative, you'll have more information, and this thing will, understanding this part will improve better. So right now, if you look at f prime, this is the x-axis, this is the y-axis. So all these values here are positive, right? They're like the y values are positive. So that tells us the slope of the tangent line is positive. That's one. But you see, it is kind of decreasing, right? And it is kind of, it starts kind of steeper here, but less steep as it goes, right? So this information allows us to pick the other choice of the slope of the tangent lines are positive. The tangents are becoming less steep. So the tangent, if they are less steep, then the tangent lines lie above the curve. So the tangent line here are the curve, let's say above the curve, just like the other example we did previously. That's what it means above the curve. And we say if it's above the curve, then you have too large, or maybe we say to match the notes, but in the homework they say too large, overestimate, an overestimation there. But in the homework they use too large. So number 12, now a similar case, but you're given g of 1 is -2, but here instead the graph you're given the derivative as a formula, which is okay because this is a is 1, so you can use 1 there to find the value there. You can use it again in the tangent line approximation or linearization or linear approximation, whichever one we use. And we find that although we don't know what g of x is, we know now how it should look near 1, right? Then we use that for 0.99 and 1.01. So these give us the ideas about, of course, the heights at the function. And looking at this tangent, square root of x squared plus 15, that's always going to come up to be positive. And when we look a little more detail about this one, so if we use a 2, 2 squared is 4 plus 15, 19, the square root, you're going to find that this thing is getting steeper. So if it's getting steeper, then the lines, these tangent lines lie below the curve. And if it's under the curve, then it is an underestimation. Right. Okay. Um, Everything else in the homework should be kind of straightforward. This is not, this is kind of an application to understand where we use these things. So we talked about two topics, a linear approximation and differentials, right? Okay, thank you.